Hello everyone, welcome to second chapter, that is fluid pressure and its measurement. So first we will start it with the introduction. Okay, so let's discuss what is the pressure. Okay, let me write it with pressure. What is pressure? Okay, so if we talk about pressure, then the definite pressure is defined, or pressure intensity is defined as is defined as force exerted force exerted on a unit area. Okay, and if you want to talk a bit like in more clear way, so I can say that it is normal force exerted. Okay, I can write here normal force exerted on a unit area is your pressure. So we can write our pressure P, which is represented by P, is equal to dF by dA. Okay, where like your dF is your force acting on infinitesimally area dA. Okay, on a very small area dA. Okay, now there are some points I would like to mention here. There are few points related to your pressure only, so let me move it here. Okay, this is your basically first point. If I talk about like this definition is your mathematically. Okay, mathematically. Okay, now if I want to talk uh, in a physical term, so physically pressure is created created due to striking of striking of molecules over molecules over a surface due to over a surface. Okay, now due to striking there is there is change in momentum force. There is change in momentum, or I can say that change in momentum. Okay, and due to this due to this change in momentum, force is generated over surface. Force is generated over a surface. So this is the physical meaning of pressure. Okay, due to like striking of molecules over surface, what happens that the molecule change, and due to change in momentum of the molecules, a momentum force is transferred or generated to the surface. This is on the basis of your second we know that Newton's second law. Okay, now there are few more points I would like to mention here. Now the pressure is comprehensive in nature. Comprehensive in nature, and it is scalar. Okay, so there are two important points. Pressure is comprehensive and scalar. Okay. Okay. Now, one more point I would like to mention here. Sorry. In like strength of materials, we have like studied about Mohr circle. Okay, so there also I mentioned earlier that pressure is represented by a point on negative side of Mohr circle, Mohr's diagram. Okay, so these are the few important points regarding your introduction of pressure. Now let's talk about what are the different units of your pressure. In which term your pressure is measured. So we will talk about units of pressure. Units of pressure. Okay. Okay. So there are of course different units. So first is your 1 Newton per meter. Okay. Which is also called as your Newton per meter square. Okay. Newton per meter square. Let me write in Newton per meter square, which is also your one called as Pascal. Okay, Pascal. Now your you have one bar, measurement of pressure in terms of bar, and this one bar is equivalent to 10 to the power 5 Pascal. Okay, or is equal to 100 kilopascal. Okay, next unit I can talk about your kgf, 1 kg force per centimeter square. Okay, this can be written as your 9.81 into 10 raised to power minus 4 Pascal. Okay, next you can talk about lbf, 1 lbf in pound for okay, lbf per inch square. Okay, per inch square. Okay, this is your pound, basically pound per inch square, pound force lbf. Okay, and this is your basically represented by 1 pound per square inch psi. Okay, this is your American unit. Okay, if I want to convert it into kgs, so I can write your 1 lbf is equal to 0.453 kg force divided by, if I want to convert inch into centimeter, so I can write it as 2.54 square centimeter square. Okay, and similarly I can write your 1 psi is equal to, I can convert it into Pascal also. Okay, is written as your 6894 Pascal. Okay, this is a near. Okay, and sorry, this should be a 10 power 4. Okay, now there are like 1 torr. If I talk about 1 torr, so 1 torr is equal to 1 mm of Hg. Mercury, from mercury, using mercury manometer, we can measure 1 torr is equal to 1 mm of Hg. Okay, now there are different type of pressures, like we generally measure your atmospheric pressure, your gauge pressure, absolute pressure, or vacuum pressure. Same pressure can be represented in terms of different term. Okay, so we will discuss that now. So let me mention this topic here. Types of pressures. Okay, so of course, as I mentioned, there are 4 types of pressures, so we will see them one by one. So first one is your atmospheric pressure. Atmospheric pressure. Okay, so if I talk about atmospheric pressure, so it is basically represented by your PATM. PATM. Okay, now this atmospheric pressure is the pressure exerted by the environment the environment or by environmental air or mass is known as atmospheric pressure. Okay, and this atmospheric pressure is measured by a device known as by using or measured using device called barometer. Okay, so we will see what this device barometer is in our further studies. Okay, but let's first complete this topic. So second type of pressure which we generally see is your gauge pressure. This is most widely used gauge pressure. Okay, so this is represented by gauge pressure. Okay, represented by your P gauge Okay, so this is all those pressures which are measured with respect to atmospheric pressure are known as your gauge pressure gauge pressure. Okay, second point, while measuring gauge pressure we assume your PATM is equal to 0, atmospheric pressure to be 0. Okay, only then we proceed with your gauge pressure. Okay, now your gauge pressure can be positive or negative. Okay, so let me highlight it here. Okay, can be positive or negative. Now pressure less than atmosphere, pressure less than atmosphere, or we also call the pressure less than atmosphere to be vacuum pressure. Vacuum pressure are known as are taken as negative gauge pressure. Negative gauge pressure. Okay. Now we move to our third type of pressure. Third type of pressure is your absolute pressure. Absolute pressure. Your gauge pressure was measured with respect to your atmospheric pressure. Now your absolute pressure is measured with respect to your zero pressure. Okay. P absolute. Okay. So, or pressure measured with respect to zero pressure, with respect to zero pressure line are known as your absolute pressures. Okay. Now these absolute pressures are always positive. Absolute pressures are always positive. Okay. This is your always positive. Okay. Your vacuum pressure is negative gauge. Okay. Now there is a fourth type of pressure. Sorry. Our next type of pressure, that is our vacuum pressure. Vacuum pressure. Okay. This vacuum pressure is represented by using our P vacuum, P VAC. Okay. Now all those pressures less than atmospheric pressure are known as your vacuum pressure. Okay. Now let me depict this in your graphical way. So let's consider a zero line first. Okay, wait a minute. So let me draw a zero line here. So let's say that this line here is your zero pressure line, or we can also call it your absolute zero, or we can also say it as complete vacuum. Okay. When, like, if you consider a system but there is nothing inside a system, that state of pressure will be called your zero pressure or complete vacuum. Okay. Now let's say this is a pressure line. Okay. This is a pressure line. Okay. Pressure P. Now let's say that this line here represent your atmospheric pressure. This is your PATM, atm. Okay, atmospheric pressure, atmospheric pressure. Now to like see what are all these pressure mean, okay, how to like uh, what are the definition define here. So we will see here in your like we consider 2 points first. We will calculate our pressures at these 2 points using different methods. Okay, let's say this is your point A. Okay, and let's say this is our point B. Okay, or let me like confine it. Okay, so let's say that I want to calculate the atmospheric pressure first. So from here to here, this is your PATM. From here to here, this is a zero pressure line. This here is your PATM, atmospheric pressure. Okay. Second, if we talk about the gauge pressure, so if I want to calculate the gauge pressure of A, so I will start from atmospheric pressure. Okay, and I will reach this point. Sorry about that. Okay. Now when I reach this point, so this length will be our P gauge at, this is your P gauge basically. Okay, P gauge at point A. Okay, now if we talk about point B, so from here if I move in downward direction, and so this distance will be our P gauge at point B. Okay, now if I want to talk about your absolute pressure, let me choose a different color for this. Okay, so if I want to talk about absolute pressure, so absolute is measured from zero pressure line, so from here to here. So this pressure, okay, so there is some, okay, so this pressure will be your, from here is from zero pressure line to up to point A. This distance will be our P absolute at A. Okay, and this will be your P absolute at B. Now if I talk about vacuum pressure, so vacuum, all those pressure less than that of atmospheric. Okay, like if I talk about this gauge pressure here. Okay, so originally what will happen, this gauge will be our negative value. Okay, and if I write it as like positive, so I can say that this distance is P vacuum in positive. P vacuum will be positive here. Okay, so if I say P gauge is equal to minus 10 Pascal, so P vacuum will be 10 Pascal. Okay, and that P vacuum only be eligible for point B only. It can't be written before point A, because point A is your like above atmospheric pressure. I hope you understood till here. Okay, let me remove these things here now. Okay, and this will be also a P vacuum at B. Okay, but P gauge will be negative, P vacuum will be positive. Okay, this term here will be like positive, this term here will be your negative. Okay, now if I want to write so if I talk about atmospheric pressure 1 atmosphere, so like let's talk about the value of 1 atmosphere. What is the value of 1 atmosphere? So 1 atm, or before that let me like write the relation between your absolute and gauge and vacuum pressure, atmospheric pressure. Okay, so P absolute is equal to P atmosphere plus P gauge. Okay, so this relation will be always applicable. Okay, Now what you have to just keep in mind that while using gauge pressure, always consider sign convention. Okay, while using P gauge, always always take with sign, with sign. Okay, positive or negative. Okay, now one more thing, we can also write your P absolute is equal to at P atmospheric minus P vacuum. Okay, so here what will happen if P gauge become minus P vacuum, as I mentioned earlier. Okay, so we will go in our whole lectures, all the lectures we go with this formula only. Okay, next there are like as I mentioned earlier, what one atmosphere is defined using various one atmosphere have various values, so I will mention them here. So one atmosphere is equal to 760 torr torr is equal to or m of fg or mf of hg. Okay, this is also equal to your 1.01325 bar is equal to your 10.3 meter of water column is equal to 14.7 psi. Okay, so these are some values which we will frequently use. Okay, okay, now there is one more important point, let me write it here only. So if we talk about BP machines, then device used in case of your BP machine is your Cefig sorry Cefigmo Cefigmo manometer Cefigmo manometer. Cefigmo manometer. Okay, now we will start our next topic, that is Pascal's law. So Pascal's law is defined by different statements. So let me first define it mathematically. So mathematically, if I talk about mathematically, so pressure, definition of Pascal law is pressure at any point in a static fluid magnitude pressure at any point in the static fluid has same magnitude in all directions. The second point, if I talk your like we have already discussed your mathematically. If we talk about in physical term, so physically pressure applied at any point, applied at any point in static fluid, in static fluid is equally transmitted, equally transmitted transmitted throughout the fluid, throughout the fluid. It means that in a fluid, like in a static fluid, if you apply a pressure at any point, that same amount of pressure will be transmitted throughout the throughout the fluid. Okay, so what does this mean? This means that pressure in the static fluid, it means that pressure in the static fluid at any point is independent of orientation, independent of orientation. Okay, now if I want to prove this, so let's consider an arbitrary fluid element. Okay, so let's consider system first. Okay, let's say this is your free surface of the water. Okay, and below the free surface we are considering, let's say, an element at this point. Okay, and if we enlarge the element, so let's say it will be something like this. Okay, okay, now let's rename these points. Let's say this point is A, B, C. This angle, let's say, is our theta, and of course this angle is 90 degree. Okay, let's say that this distance is your dx, or I can also write it inside. Okay, this is your A, B, C. This angle, let's say, is theta. Okay, this is 90 degree. This distance is your dx. Okay, and this distance is our dy. Okay, now let's say this length of the wedge is our ds. Okay, now and this ABC is your element. Okay, now let's say this dimension is our dx. Okay, this dimension is dy, and this dimension is our ds. Okay, now I can say that this angle is our theta, and of course this triangle is right angle triangle. The pressure in upward direction is our py. Okay, the pressure in horizontal direction is px, and pressure at any orientation theta, let's say this pressure to be pz. Okay, so this pressure to be pz. Okay, now this pressure pz can be like made into two orientations, vertical, like two components, vertical and horizontal. And since this angle is theta, so we know that from since this angle is theta, so we can write here this angle is also theta. Okay, so the vertical component will be pz cos theta. Okay, and horizontal component is here, or even if you don't consider this, so we can like write it without your force components. We can directly write using the area. Okay, so from here we can write that dx is equal to ds cos theta and dy is equal to ds sin theta. Okay, so let's consider arbitrary fluid element. Arbitrary fluid element in wedge shape. Okay, in static fluid. Static fluid. Okay, so Pascal law is for your static fluid. And consider width to be 1 unit. Width to be unity. Okay, and that is of course perpendicular to plane. Okay, now we will do our force balancing in x and y directions both. Okay, so force balance in x direction. Okay, and force balancing in y direction. Okay, so for x direction we will write summation of fx is equal to 0. Okay, now we know that force is equal to pressure into area, so fx will be like in this direction. Let's consider force to be positive in x direction. Okay, so let's say this is our x and y. This is your x, positive x, this is your positive y. Okay, so your summation of x will be px into your dy times of 1. Okay, area of cross section. Okay, and if we come to this direction, then pz sin theta will be acting on this dy surface, so we can write it as minus pz sin theta, pz sin theta, and it is acting on the area, your ds area. Okay, and area, sorry, ds into 1. Okay, this is equal to 0. If we write this is equal to 0, so from here if we solve this, so we can write your px into dy minus pz into your ds sin theta. Ds sin theta is equal to dy. Okay, so from here you can write px is equal to pz. Okay, this is your first equation. Okay, now if I talk about your balance in y direction, so in y direction we have PI pressure is acting on your dx times of 1. This is your surface area minus pz cos theta is acting on your ds in times of 1. Now this force should be 0, of course. For okay, of course, there's one more thing, like weight of the fluid will be acting in downward direction. Okay, so we have to also subtract weight minus weight of element is equal to 0. Okay, but what happens, like since this dimension is very small particle we consider, so we say that our weight of the element is negligible. Okay, so we put it is equal to 0. Okay, so from here we obtain py into dx minus pz. Now ds cos theta is here equal to dx. Okay, so from here we obtain py is equal to pz. Okay, so this is the relation. This will be 0 at for a point. Okay, now let's say this is our equation A, this is our equation B. So we can write from A and B, from A and B we can write our px is equal to py equal to pz. Okay, okay, so this here is your Pascal's law. This is your Pascal's law. Okay, now with respect to your Pascal's law, we have an phenomenon or basically a concept of hydraulic lift. Okay, so let me discuss it here also. Hydraulic lift. Hydraulic lift. So what is hydraulic lift? This is a combination of your like thick and thin limbs. Let's say we have a system that is like this. So it's something like this. So we have a thin limb and we have a limb with larger cross section. Okay, okay, and let's say it is filled with the fluid. Okay, so something like this. Okay, like it will be on same level. Okay, on the same level, both limb will be at same water level. Okay, so this is water. Okay, now let's say we have a car. This is generally used for car lift or heavy weight lift. So let's say we have a car here and the car is put on this larger, we can consider a type of like piston cylinder arrangement type. Okay, so let's say this is a piston. Okay, so this is our piston. Okay, and this is our smaller piston. Okay, so if we apply some force, let's say F, some force F here. Let's say we apply some force F here, okay, and weight of the vehicle is our W, okay. Small a is the area of cross section for the smaller tube, and capital A is the area of cross section for your larger tube. Now let's say that due to this small force, the moment of piston is by the amount x, okay, by amount x. Now what will happen, this like due to this, like water is let's say this is water, so water is incompressible, hence this platform will move up by a distance, let's say y, okay. And what else we know, that our pressure at each and every point in a static fluid is same, okay. So from here we can write that force pressure at this point and this point should be equal. So we can write that F upon A is the pressure in the shorter limb is equal to weight upon area, that is our pressure in your shorter limb, okay. Now what else we can write from here, we can conclude that since F and one more thing, like since this area is larger, so this weight would be larger, and this area is smaller, so this F should be smaller. So by applying the less force we can lift the heavier weights here, okay. So what we can say, since F is less than W and x is greater than y, this moment will be larger, because like the same volume for here have in the thinner limb will have more height than compared to your thicker limb, okay. So from here we can say that work done for both pistons is same, both piston is same, it means that energy is conserved, okay. So from this we can see that for a smaller force F is required, for lifting a weight W, but conservation of energy is not violated, okay. We can say that energy is conserved here, energy is conserved, okay, because this smaller force moves larger distance, while your larger force moves small distance, hence work done for both are same, okay. Now let's talk about hydrostatic law. So this hydrostatic law was given by Torricelli, and this law states that variation of pressure of in vertical direction in a static fluid is directly proportional to specific weight, okay. So to if I want to indicate it mathematically, so let's do a small derivation for this first, okay. So let's consider a surface again, like this is a free surface, and we will be considering an a fluid element, okay, but here we will be considering a 3D element. Let's say this is, so let's say this is a fluid element, okay. So this is a fluid element, fluid element, okay, and this is our upper face, this is our downward face, okay, up face and down face, okay. Now let's say that area of cross section is, let's say, dA, okay. So we can write that vertical downward force acting on this surface, we can write it as, let's say, if P is the pressure here, then P into dA is the force, vertical downward force, okay. Now let's say that this height, like the height of the fluid element is dH, okay. So the vertical force acting at this height will be P plus dP, P pressure here, and change in the pressure dP, P plus dP times of dA. This is our upward force, and of course the weight of the liquid will be acting along. This is our weight of fluid element, and this value will be equal to rho g, okay, times of volume, that is dA times of dH, okay. So for fluid at rest, it should be in equilibrium, so we can write summation of F is equal to 0, okay. Now if I want to write summation of A in vertical direction, let's say, so I can write it as P into dA is our downward force, okay, plus weight of the element, that is rho g dA into dH is our downward force, minus upward force, that is P plus dP times of dA, and this is our net force, and this force should be equal to 0, okay. So from here I can write like PdA will be like obsoleted by this term, so we will be left with rho g dH is equal to dP. So from here we can write that dP by dH, or let me write dP by dH is equal to specific specific weight, sorry, okay. So this is our hydrostatic law. Hydrostatic law, okay, and this hydrostatic law is valid for both compressible and incompressible fluids. Compressible and incompressible fluid, okay. So now if we look at the figure, if I look at the figure, so in this we will see that we are moving from upward, like from above we are moving in downward direction, okay. So let me like move to second part, that is pressure at depth h, okay. And first case we will be considering is our incompressible fluid. Incompressible fluid, okay. So for incompressible fluid, we know that our density is equal to constant. Okay, so let's consider. Let's say this is our free surface. Okay, and we want to find our pressure at a point. Let's say this is our point. Okay, A. Okay, and it is at like h depth. Okay, and so let's say rho is the density of the fluid. Now we can write our hydrostatic law. We know that is equal to dp by dh is equal to rho g. We know this. Okay, so if we integrate this, so we can write it is dp is equal to rho g dh. Okay, and we can integrate it from, like, if we move from this point. Okay, if we consider to move from this point, so we know that h is equal to this 0 at this point and h at point A. Okay, and at this point we know that our pressure is equal to p atm. Okay, so from p atm to p at A. Okay, and this pressure is p is absolute pressure here. Okay, so from here we can write what we can write. We can write that pa is equal to, or pa minus p atm is equal to rho gh. Okay, so from here we can write our p a is equal to p atm plus rho gh, or we can also write, and this pa is actually absolute. Okay, and we can write pa gauge is equal to rho gh. Okay, so these are the points you should know. Okay, so from here we can say that on the same horizontal level, they, like, if I keep the h same, so there won't be any pressure difference. That if I keep the value of h constant, so pressure will remain constant. Okay, and if I change the, like, with the height, the pressure varies linearly in case of your incompressible fluid. If I want to let's say draw the variation. Okay, so let me make some space here. Okay, let's say if I want to make some variation here, like draw the variation of pressure here, so how can I draw? Okay, so let me draw it here. Okay, so let's say here and here, two variations I will draw. Okay, or I can also draw one variation only. Okay, so look at here now. So if I talk about at the top, so here the pressure is our p atmosphere. Okay, and since we are increasing the h as we are moving deep inside the fluid, so what is happening here, our pressure is also increasing. Okay, so it should be something like this. Okay, and here the pressure at the bottom, so this is equal to our p atm plus rho gh. Okay, and this is equal to your okay, so this is your pressure variation. So if if you want to, like, this is the indication of your absolute pressure. If you want to, like, say denote only the gauge pressure, so you can start from here. Okay, so pressure you will consider at top is equal to 0. Okay, and one more thing, like if I talk about the variation of density. Okay, so we know that variation is like density at height, rho gh. Density and height both are the varying function, because g will remain same. Okay, so if I talk about, let's say, from here to here, so if I consider two different densities, let's say this is a plot. Here I will be showing you the gauge pressure variation only. Okay, Okay, and this is your second variation. Both variation is possible, are possible. Okay, we know that. Okay, okay, okay. So what we can say, let's say this is for your density rho 1, this blue one is for density rho 1, and this yellow one is for density rho 2. So we know that the pressure in case of rho 2 is higher and pressure in case of rho 1 is lower. So we can say that our rho 2 should be greater than our rho 1, because on the same height the pressure in case of rho 2 is larger than comparison to that of rho 1. Okay, so as rho increases, your slope decreases. Okay, I hope you understood till this point. Okay, now we will be talking about our second one, or before that, one more thing I would like to mention here. And one more thing, like you should remember this formula, always remember this formula, that P gauge is equal to rho g h. So this is your pressure relationship. Okay, you should remember this formula, and of course you know that unit is your either Newton per meter square or Pascal. This is basically your hydrostatic law. So as we move vertically down, the pressure increases as plus rho gh, and as we will move upward vertically up in the fluid, your pressure will decrease by by rho gh. Okay, so as since we have already discussed incompressible fluid, so let's discuss compressible fluid now. Okay, so what will be the variation for in case of your compressible fluid? So second one is, so if I talk about compressible fluid, so in this we will generally consider your ideal gas. Generally consider this for ideal gas. We will consider ideal gas. Okay, so and one more thing, we will treating medium as isothermal. Okay, so we know that our dp by dh is given as, okay, and one more thing, like if we consider let's say here our consideration is like this. So this is our ground. Okay, and we are moving vertically upward in upward direction. Okay, so in case of vertical, when we are moving downward, I mentioned you that our increase in pressure is rho gh, and when we move down upward, our decrease in pressure is rho gh. So here dp by d h will be written as minus rho g. Okay, so since it is minus rho g, we will proceed with this. So we know that in case of ideal gas, for ideal gas, we know that our P is equal to rho RT. Okay, so we can write rho is equal to P by RT. Okay, and I can write dP by dH is equal to minus P by RT times of G. Okay, so if we rearrange these terms, so we can, from here I can write dP by P is equal to minus G by RT times of dH. Okay, now integrate both sides. So at H is equal to 0, our pressure was 0, or let's say that at H is equal to 0, our pressure is equal to, let's say, P naught. Okay, and temperature is equal to T naught. And since we have mentioned here that or we can like ignore the temperature term, because we have already mentioned here that the process is isothermal. So H is equal to 0, pressure P naught, and pressure P at height H. Okay, so if we solve this, so from here we obtain ln P by P naught is equal to minus GH by RT. Okay, so if we solve this, so from here we will obtain our P is equal to P naught times of e की power minus G by RT times of H. Okay, so from here what we can see, we can say that the variation of pressure in case of pressure like atmospheric pressure, or we can say that compressible fluid, the variation of pressure is exponential. Okay, so if I want to draw the variation, so it should something like this, it should be something like this. So let me remake this. Let's say this is our height H. Okay, so our variation should something like this. Okay, so this pressure should be P naught. Okay, and as we move upward, the pressure is decreasing. Okay, because the exponential function is negative, it should be something like this. Okay, so this equation is applicable for your isothermal and compressible. Okay, now let's consider this 6 cases. The 6 type of containers are filled with your fluids. Okay, and let's say H is the level of water level inside every type of container. Okay, so if we talk about the pressure at the bottom, that is point A, B, C, D, E, F. Okay, although like the quantity of water inside each container will be different, and so will be the weight of the container. But if we talk about the pressure, so we know that our pressure like the dp by d rho is equal to rho g from your hydrostatic law. So we can say that like here we can write that Pa will be equal to Pb is equal to Pc is equal to Pd is equal to Pe is equal to Pf. Okay, like the pressure at each like for each container at the bottom will be same irrespective of their shape and size. Okay, so this is known as our hydrostatic paradox. Okay, I hope you understood till here. Okay, so like your pressure variation does not depend on your shape and size, on which how is the shape of the container. Okay, like here it is like some round about manner. Here it is like circular at the bottom, and here the large volume water as at the upper level. Okay, what it depend on pressure is the what is the difference in height between the 2 points you are measuring. Okay, and of course we are talking about when the fluid is in static condition. Okay, now there are two more points I would like to mention here. So first point is regarding pressure head. So the vertical height from the free surface above any point in the liquid is known as your pressure head, and this pressure head is given by H is equal to P by rho g. This is your pressure head. Now if we talk about definition, free surface above any point in the liquid. So from any point up to your free surface is your pressure head. Now the second point is regarding your like conversion of fluid column. Of fluid column. So let's say there are like there are two different type of liquid, okay, and both liquid like develop the same pressure, okay. So let's say that your pressure is equal to rho 1 g h1 and is equal to rho 2 g h2, okay. So for two different liquids having different densities, you will have different column height or different pressure height, different column height for the same pressure, okay. So from here I can write rho 1 h1 is equal to rho 2 h2, okay. So this is your relation conversion, okay. Or we can also write it as like if I use your specific density or specific gravity, so I can write it as s1 h1 is equal to s2 h2, okay. So this is your conversion of fluid column. So if you know the height of the fluid for a given column, you can convert it into another one, okay. Now we will start with our next topic, that is pressure measurement devices. Pressure measurement devices, okay. So there are different type of devices, basically three main type of devices there. First one is your barometer. This barometer is used to measure your atmospheric pressure, okay. Second one is manometer. Manometer, okay. And third one is mechanical gauges. Okay. Now these manometers can be further differentiated into two parts, okay. One being your simple manometers, second one is differential manometer. Okay. Now if I talk about different type of mechanical gauges, or okay, so let me I will discuss them later, okay. So these are the main differentiation, okay. Now in simple manometer, you will further study about piezometer, U2 manometer, single column manometer, and in differential manometer you will study about two piezometer manometer, inverted U2 differential, and micromanometer. Similarly, in mechanical gauges, your Bourdon tube pressure gauge, diaphragm pressure gauge, below pressure gauge, and deadwood pressure gauge, okay. So we will start with our first one, that is barometer. So barometers are device which is used to measure your atmospheric pressure. Okay. Now this atmospheric pressure is also referred as your barometric pressure, okay, sometimes. Now this how to like use barometer. So let me draw a figure here. So let's consider a container. Let's say this is our container, okay, and let's say in this container we have filled some mercury, okay, and of course atmospheric pressure is acting here, okay, and here we have a manometer. So not manometer, sorry, I mean tube. Let's say this is your tube, okay. Now since it is placed horizontally, so your mercury will be also be filled inside this, okay. Now we have rotated this. Now we have rotated this. Rotate, okay. So it would be something like this. Okay, so here your like mercury level will be something here, okay. It would be something like this, okay. Now let's say h is this height is our h, okay. So since this fluid is static, so we can say that pressure at this point and this point will remain same, okay. Let's say this is your point A, this is your point B, and here is your point C, okay. So if I talk about the pressures, so pressure at A will be equal to pressure at B and will be equal to P atmosphere, because in case of static fluid pressure at the same level remains constant, okay. Okay, now if I talk about pressure at C, so pressure at C can be taken as is equal to vapor pressure of mercury. So what would happen if we consider this section only? So after like your tube is rotated, so mercury will fall due to the weight of the mercury. The level will fall inside the tube, and here the vacuum region will form. Okay, vacuum or torricelli region. Okay, and inside this region there will be your mercury vapors, okay. But for mercury your vapor pressure is very low, okay. So so this value pc is generally assumed to be 0, okay. At vacuum your pressure is 0, okay. I hope you understood till here, okay. Now if I consider like if I use your hydrostatic law, so we can write that pc minus pb pc minus pb is equal to rho of mercury into g times of h, okay. I hope you understood till here, okay. Now we can write your sorry, it should be pb minus pc, okay, because when we move downward our pressure increases, okay. So higher pressure minus lower pressure is equal to rho gh, or we can like also consider it like this. So let's consider this water column inside, okay. So let's say this is point B and this is our point C, okay. So here your PATM is acting, PATM is equal to PV, we can also write, okay, and your weight is acting in downward direction, weight, and this weight will be equal to rho g, I mean this weight will, okay, okay, so PB into A will be your force, okay, pressure force, okay, and the weight will be rho g H A, rho g times of volume A into H, okay. So if we equate both at equilibrium, both should be equal. So from here, and since we have already considered PC is equal to 0, so I can write my PB is equal to rho Hg into G into H, okay. And if we substitute the value, we know that our rho for Hg is, or I can write PATM, rho of Hg is equal to 13.6 into 10 to power 3 kg per meter cube. G is written as 9.81, okay. And in case of your like mercury, we say that 1 atmosphere is equal to 760 mm of Hg. It means that in this H will be 760 mm, so can be written as 0.761, okay, sorry, 760, okay. So if we solve this, so from here we will acquire PATM is equal to 101.325 kilopascal, okay. So this is your atmospheric pressure, okay. So this is your discussion about barometer. Now if we talk about why this mercury is used, so let me mention it here. Why Hg is used in barometer and not some another fluid like say water or something else, okay. So what happens, there are two reasons basically. So density of Hg have high density, and second point is Hg has very low vapor pressure. So Hg has high density. So what does high density mean? High density mean that your height of the fluid column will be less, okay. Height of the fluid column will be less. Like if you consider your water, so we know that for water, your height of the fluid column required for to measure the atmospheric pressure is 10.3 meter, okay. So that is 1 atmosphere is equal to 10.3 meters of water column. So if we use the barometer, so we have to like keep the tube of the length 10.3 meter, which is actually not quite accessible in the labs, okay. So we generally use Hg. And very low vapor pressure, like if there are vapor pressure, so like we have to consider PC also, okay. Here's a calculation are direct, okay, and there is no less loss of the mass, okay. Now we will move to manometers. Okay. So manometers are those pressure measuring devices which are based on principle of balancing the columns. These manometers are based on principle of principle of or sorry principle of balancing the the column of liquid. Okay, now this balancing is by done by same or different different fluid or liquid. Basically, not fluid, we generally use liquid. Okay, now these manometers are divided into two portions, as I mentioned earlier. These are your simple and differential. So simple manometers are which measure pressure at a point, and differential manometers, okay, so let me write it here only. Simple manometers measure pressure at a pressure at a point. If we talk about differential manometers, then differential manometers measure pressure difference between any 2 points, between any 2 points. Okay, so let's start with the simple manometer. So if we consider simple manometers, then if I want to write the classification for simple manometer, so in this we basically consider three setups. First one is piezometer. Second is U2 manometer. Third is your single column manometer. Single column manometer. Okay, if we talk about differential, then in case of this, two piezometer manometer. Second is inverted U2 Third is U2 differential. Fourth one is micromanometer. So let's start with your first one, that is let's start with piezometer. As I already mentioned you earlier, that the manometers are of two types. First is your simple and then differential. So we will start with your simple manometers. So first manometer I mentioned in simple manometer is piezometer. So let me start with piezometer. So if I talk about piezometer, so piezometer is basically your simple glass tube. It is a simple glass tube that is open at one end, open at open at both ends. One end of the pipe, one end of tube is connected to pipeline, to pipeline. Of course, where pressure to be measured, or whose pressure to be measured. Pressure to be measured. Okay, and whereas other is open to atmosphere. Other is open to atmosphere. Open to. Okay. So let's consider a pipeline. So I will, let's say that this is a pipe. Okay, and you have to measure pressure in this, pressure of the fluid flowing inside this pipeline. Okay, so your piezometer can be installed at any point. At any point, there is no limitation on where you should uh, install your piezometer. Okay, so I will like showing the example. I will install this piezometer at different points. Let's say this is, I have installed piezometer at the top. Okay, at the side. Okay, at the sides. Okay, so let leave it to be. Okay, okay, so let's say it's something like this. Okay, and let's consider another piezometer or a tube which is at your bottom location. Okay, so let me draw it here. So let's say that we have installed three piezometers here in this pipeline at different location, one at top, one at side, and one at your bottom. Okay, and let's say there is a fluid. Of course, if there is a pipe, there will be some fluid flowing inside the pipe. Okay, now if I want to measure the reading here, so in all three manometers, like the liquid level will be the same. Okay, okay, so your level of liquid inside three tubes will be same. And if you want to like measure the level, liquid level, like height of the manometer, so we can do it with respect to center. Okay, from center we will measure the height of the free surface inside the tube, and this will be your manometric height, or your column height of piezometer. Okay, and of course say like there are some limitations. And one more thing, if I want to write pressure at, let's say this point, let's say is A, then if I want to write pressure at A, so I can write it as rho gh. And if, of course, the rho is the density of the fluid here, rho g, and h is the column height. Okay, and of course this is your gauge pressure here. Okay, now uh, there are certain limitations for piezometer. and these limitations are: first is they cannot be used to measure very high pressures, very high pressures. Because what will happen if your pressure is very large, then this column height will be will be proportional to your pressure. From here we can say that pa is proportional to height h. So for very high pressure, the height h required will be very large, and to like install the manometers of those height won't be like realistic. Okay, so we generally use piezometers to measure your small pressure small pressures. Okay, second limitation if I talk about, then this piezometer cannot measure pressure of a gas pressure of a gas. Since this piezometer is like open to atmosphere, so like if we install the piezometer in a pipe which is carrying gas, then the gas will be lost to your atmosphere. So the second limitation is gas pressure cannot be measured. If we talk about third limitation, then vacuum pressure. Here we will talk about vacuum pressure cannot be measured, or cannot measure vacuum pressure, cannot measure vacuum pressure. Okay, in case of vacuum pressure, outside air will be sucked inside the pipe. Okay, so these are some limitations, and to overcome these limitations, we move to our next type of simple manometer, that is your U2 manometer. Like here I mentioned first piezometer. Now second is, sorry, second if I talk about, then it is U2 manometer. U2 manometer. Okay. Now in case of U2 manometer, what happens? Okay, so let me draw a diagram first. So let's consider the same pipeline. Okay, so we have to measure the pressure inside this pipe. Okay, let's say this is point A. Okay, and U2 in U2 manometer, what we do? We install a your manometer is of U2 type. Let me draw it here also. So okay, so let's say it is something like this. Okay, and this is your U2 manometer. It is like this. Okay, okay, let's say that the fluid or of density rho is flowing inside your pipe. Okay, okay, and what we do, we actually fill this manometer with a liquid of higher density. Like we will fill this up with a higher density fluid. Okay, so here we have a higher density fluid. Okay, and let's say that your pressure of the gas is higher than the atmospheric pressure. So like this will the height difference. Okay, this will be the height difference here between the both level. Okay, okay, so let's say this is your level, this is here at this level. Okay, this height difference will be your x. Okay, And if we like, if I mention it clearly, so like let's say that initially it should be at this level. Okay, initially the like the this grain density fluid. Okay, and we generally call it manometric fluid. Manometric fluid. And this, let's say this have density rho 2. Okay, and the fluid has a density rho 1. This is your initial level. Initial level. Okay, now from initial level, this fall in the left limb and rise in the right limb, we can say that volume of liquid fall is equal to volume of liquid rise. Okay, so by this we can calculate by how much, like if we know the damage, how much is the value of your x. Okay, now let's say I want to apply your manometry here. Okay, so let's say that PA is the pressure in your pipe. Okay, and of course let me mention few more things here. Let's say that this height here from here to here is h, from here to here is your capital H. Okay, and like the both liquid level is x. Okay, and this height, let's say, is z. Okay, so I can write PA. Now if we are going downward, then while moving downward our pressure increases by your amount of rho gh. Okay, so plus now rho here is rho 1 g, and h is capital H. Okay, we have reached this point. Okay, after that we will move downward by amount of z. Okay, so again we are moving downward, so pressure will increase. Now the density of fluid is rho 2 g. Now this dimension is z. Okay, and at the base we know that by your Pascal law, your pressure at same level remains same. So pressure at this point and pressure at this point will remain same. So from here we will move from here to now your top point. Okay, so this distance total is x plus z. So I can write, now we are moving up upward, so this should be minus rho 2 times of g minus rho 2 times of g. Now h is, this will become your x plus z. Okay, now this we can put equal to 0 in case we want our PA in terms of your gauge, and if we want PA in terms of atmospheric, so we can substitute P atmosphere here. Okay, so if we solve this, so this term and this term will cancel out, like z term. Okay, so from here we will get PA is equal to PA is equal to rho 1 g h, sorry, PA is equal to, now this is your minus rho g h is equal to minus, or we can write PA plus rho g h and minus rho 2 gx is equal to 0. Okay, so from using this equation we can like calculate our pressure at A. Okay, now this is your simple manometry equation. Okay, now there is a method of jumping discontinuity. Okay, like how to use, so jumping jack method. Okay, so what we do, like for a same liquid at same level, we know that pressure is same. So from here we can directly say that pressure at this point
and corresponding this point will be same. Okay, like we have seen here that both z term like rho 2 g z, rho 2 g z minus this will be again rho 2 g z. Okay, so this term will be cancelled out again. Okay, so what we do, like since this is a like same liquid, in the same liquid at same height the pressure is same, so we like move directly from this point, we move to this point. Okay, so how we will write your pressure equation? So we will write it as pa plus rho 1 gh, rho 1 gh. Okay, now we will directly move from this point to this point, and this is again minus rho 2 gx is equal to again 0 or p atmosphere. Okay, now this U2 manometer can be used to measure both your negative and vacuum pressure. Okay, now of course the negative like to measure negative pressure, like since this is a positive pressure, so like this will move upward, this level will move upward, and this level will move downward. Okay, and in case of negative pressure, this side will the liquid will rise on the left hand and liquid will fall on the right hand. Okay, so of course up to certain limit only that it can measure your vacuum pressure, okay, or negative pressure, because after that this manometric liquid fluid will be sucked inside your pipeline. Okay, now here the problem is like we need to take the reading. Let me write it here. Limitation. So limitation is this matter require reading of of fluid at two or more points, two or more points, and what does this mean? This mean that we have to measure like reading at this left hand right limb both side. Okay, at both left and right limb. Okay, because like one side it will liquid will fall and other end it will rise, so it requires the reading of two or more point, since like your change in pressure causes a liquid to rise on the left end and uh, or fall on the right end limb. Okay, so this is your limitation here. Now there is one there are also different type of like to overcome this difficulty, like to since we should measure let's say I want to measure your reading on one end only. Okay, I don't want to measure the reading at both limbs. So for that we have another type of manometer. Okay, and the third type is your single column manometer. Single column manometer. So what is different in this manometer is that everything remains same. The difference is that, so let me like take this diagram exactly only. Okay, because major things remain same. Copy, and there are slightly change. There is slightly change in this. Let me. Okay, so I have to draw this again. Okay, so let me draw it here again. Okay, so this is your reservoir here, And again, this is similar to your YouTube only, but there is slight difference. Okay, so let's say this is your single column manometer. So what happens that your liquid is like this, like we have filled manometric fluid originally at this level. Okay, but since it is attached to a pipe, so this level will fall. Okay, so let's say, let me draw a line here. So let's say this is your initial level. Okay, and due to the pressure, your level has fallen to this point. Okay, and of course this is your manometric fluid. Okay, and your liquid level will rise in another end. Okay, so this is let's say your row m manometric. Okay, and this is your row of fluid, let's say. Okay, so one more thing, like as I mentioned earlier, that this is your reservoir. This is your reservoir. reservoir Okay, and this has a cross section area of A, like cross section area of this reservoir is A, and let's say that for tube the cross section area is A, small a. Okay, and due to this pressure, let's say the H1 is the height from this point to your initial level. This, let's say, height is H, and this your liquid level fall is, let's say, delta H. Okay, okay, and here the rise in liquid level on this side, let's say this is equal to your, or this is your H1. Let's say this is your H1 and this is your H2. Okay, so as I mentioned earlier, that volume of rise is equal to volume of fall. Okay, so from here I can write that A into delta H, okay, is equal to small a into H2. Okay, so from here we can write that small a upon capital A is equal to delta H upon H2. Okay, now let me apply the manometric equation here. So I can write that PA plus rho density of fluid into G into H1 plus delta H. This is your total like fall. Okay, na, height of fall is equal to, or sorry, now we will move from this point directly to the corresponding point in the other limb. So there we will move upward now. So minus rho m times of G times of H2 plus delta H. Okay, now what we can do here, so here we can write that PA is equal to rho m G H2 minus rho f G H1, okay, plus delta H times of G rho m minus G rho f. Okay, now since this delta H will be very small here, delta H is very small. So due to this delta H being very small, what will happen And let me write one more thing here, right? This capital A is very greater than small a. Okay, so from here we can say that our delta H will be very less than that of your H2. Okay, so what we can do, we can like neglect this term completely here. So from here we have obtained PA is equal to is equal to PA is equal to, so we have get PA is equal to rho m times of G H2 minus rho f times of G H1. Okay, now generally this single manometer, column manometer is used to measure the pressure of your gas. Okay, so in that case what happen, your rho f is very small, and generally what happen that the pressure inside this will be equal to pressure here also. Okay, at equilibrium at both point the pressure will remain same, so we generally neglect this term. Okay, so for gas is we get PA is equal to rho m G H2. Okay, and this is your actually the like not a true, like if we want actual pressure, so it should be plus delta H times of rho, sorry, G times of rho m. Okay, also like we can although we can neglect the pressure difference from this point to this till here, we have to consider that of the this exactly true point. Okay, but if we, this is your PA, let's say true. Okay, and this is your PA approx. So okay, so it will be your rho mg H2. Okay, so there is a concept of error inside your single tube manometer. So is given by PA true minus, or percentage error, let's talk about percentage error. PA true minus PA approx divided by PA true into 100. And if we substitute these values here, so PA true is your this value, PA approx is this value, so if we minus this, so we will obtain this term. So rho mg times of delta H upon rho mg times of g times of H2 plus delta H. Okay, so from here we will obtain it. Okay, and into 100. So from here we can write it as delta H upon, now H2 plus delta H, I mentioned here that H2 is very greater than that of delta H, so I can directly write it as your H2. Okay, into 100. So percentage error is your delta H by H2, or we can also write delta H by H2 is your small a by capital A into 100. This is your percentage error percentage error. Okay, now your this limb can be your straight limb, or we can also like consider this to be your inclined limb. Okay, now in case of inclined tube, so we have a sensitivity equation. So let me draw it here. Like if I talk about inclined tube, inclined tube. Okay, so let's say that as I have like, let me take this example here. Okay, so let's say that we are taking, so take the symbol this much only. Okay, copy, and I will use the same diagram here. Okay, there will be slight difference. Okay, so let's say that I have considered this limb to be inclined like this. Okay, and the inclination is angle theta from horizontal. Okay, so of course the fluid will be filled up to same level only. Okay, up to same level only the fluid will filled like this. Okay, and this side of course will be your H. Okay, now this length of the slanted length will be your H by sine theta. Okay, so we write your sensitivity sensitivity is equal to 1 upon sine theta for this inclined tube, 1 upon sine theta. Okay, and generally what happens that this sensitivity, like if we this theta is kept between 15 degree to 20 degrees, and if theta decreases then sensitivity increases, we can see from this equation only. Okay, and if sensitivity increases then what will happen, your error will increase. Okay, I hope you understood till here. Okay, because higher the sensitive, like if the more slanted this inclined tube will be, the larger the fluctuation of the fluid level will be inside the tube, and this fluctuation will be like due to your like leveling, due to vibration from anything, due to slight difference, slight disturbance, the fluctuation inside the manometric height will be large. Okay, so because of that, in inclined tube, as your theta decreases, your error will increase. So with this we have discussed our simple manometer. Now let's move to your next part, that is differential manometers. Now in case of your differential manometers, I have mentioned that it is used to measure the pressure difference between 2 points in the same pipeline, or pressure difference in two different pipelines. So let's start with the first kind of your differential manometer. First is your two piezometer, two piezometer manometer. Okay, okay. So it's like this. So at the two different locations we install our piezometer. Let's say this is location A, or pipe A, this is location B, or pipe B. Okay, this is our center line. Now we measure, like let's say the fluid inside A, and let's say it reaches up to this level. Okay, let's say fluid inside B reaches this level. Okay, okay, so this different in level from here and here. Okay, this is your height difference. Let's say this difference is your x. So by calculating these two heights for the two manometers, or let instead of this, let me write here, this is your the pressure head at A is your HA, let's say this head is your HB. Okay, so the two piezometer manometer is used to measure pressure at when pressure when pressure at each point is each point is small. Okay. Second point, I can say that cannot be in case of gases, cannot be used for gases. Okay, so these are your same limitations as we have discussed for piezometer. Okay, now after that we move to our second one, that is inverted U2 manometer. Inverted U2 manometer. So this inverted U2 manometer is basically similar to your two piezometer manometer, but there is slight difference. Let me draw it here. Like if it is like this, then the difference is okay. So there is some manometric fluid inside this. Okay, or like sometimes it is also simple air. Okay, sometimes it is manometric fluid, and let's say this is your initial level. Initial level. Okay. Okay, and of course pipe A, pipe B, and due to its pressure, let's say that here it reaches up to this point and here it reaches okay up to this point. Okay, and let's say this height difference is your h. This height difference is h. Okay, and this rho m is your less than that of rho a or rho b. Okay, because if it is higher than density of a or b, then what will happen? It will be sucked inside the pipe. Okay, it will it will not stay on the top, it will fall into the pipe. Okay, now if I want to write, let's say your piezometer manometer equation, so I can write Pa minus, now let's say this is rho 1, this liquid is of rho 2. Okay, Pa minus rho 1 G. Now let's say that this height is your H1. H1, and this height is your H2. Okay, P1. Now we are Pa minus we are moving upward, so minus rho G H1. Okay, now here it is manometric fluid, so again we are moving upward, minus rho m G H. Okay, now since we have reached here, so we will consider your density of this fluid rho 2. Okay, and since I'm moving downward, so it will be rho 2 G H2, and this will be equal to your PB. Okay, so from here we can calculate our pressure difference. It is Pa minus PB we can calculate. Okay, so this is how we generally use your manometer equation. Okay, now third type of, if I talk about differential manometer, then that is your U-tube differential. Okay, again let's say there are two type of tubes, tube A and tube B. Let's say this is the A, this is your V. Okay, and we have installed a U2 manometer between both points. Okay, let's say it is something like this. Okay, we have installed your manometer between A and B. Okay, now of course there will be manometric fluid here. Let's say this was your initial level, and now this is your final level. Okay, let's say X is the difference in the level. Okay, X. Okay, of course again we are similar in and one more thing, this rho m is greater than your rho a or rho b. Okay, now we can again apply the manometer in same way as we have used earlier, and I won't be mentioning here. Now if we talk about our third type of manometer, as I mentioned here, that is your mechanical gauges. So in mechanical gauges, if I talk about different types of gauges, so let me mention them here. First is your Bourdon tube, pressure gauge. Second is your bellows pressure gauge. Third is your diaphragm pressure gauge, and one more, that is dead weight pressure gauge. Okay, so with this we have concluded our chapter fluid pressure and its measurement. Now in next lecture we will be discussing about your few questions related to this topic. So thank you.